much for joining us today for our Grasp on Robotics series. My name is Mark Yim. I'm the faculty host for today's talk. As a quick reminder, the previous recordings are available on YouTube our YouTube channel, and you can get to that from our Grasp website. If you're joining us by Zoom, please submit your questions using the Q&A button at the bottom. They will be answered during the Q&A panel session. We've got two of our panelists here, Tom and Jasleen. Tom is a PhD student with Ani Xie, and Jasleen's a RoboMasters student. So we are very fortunate today to have Rod Brooks. It's an honor for me to introduce him. He is currently the founder and CTO of Robust AI. We started in 2019. Before that, he was the founder and CTO of Rethink Robotics. That was acquired by Han in 2018. Before that, he was founder and CTO of iRobot, that had an IPO in 2005 and raised about $149 million. So he's had quite a lot of success in these companies. And somewhere in there, he was also a professor at MIT, which is what, of course, most of us know him by. He was he led CSAIL, the Computer Science AI Lab, for about 10 years. I forgot when he left MIT to be the full-time business stuff. But
2010.
2010. So that was a while ago. He is a member of the NAE and also a fellow of the Australian Academy of Science. He was featured in a film in 1997 called Fast, Cheap, and Out of Control. That's when I was in school. He was like, he was the thing. He was like the person who changed. Everyone was thinking about robotics when he started doing all this behavior-based things, and everyone was saying, "Oh my gosh, he's changing AI. He's a heretic. He's like changing everything." It was so it's a great honor to have him here speaking today. So please welcome Rod Brooks.
Okay, thanks, Mark. And thanks for having me here. I stopped giving talks even online during COVID, so this is a sort of a reintroduction, and I may be a little rusty. So we'll see how it goes. There were a lot of things I wanted to respond to, but I'm not going to. So I want to talk about exploration and exploitation in academic research, and really it's two talks. One is how to be a better exploiter in robotics, how to exploit what's out there and do stuff now, but also some deeper questions on things that I think should be being explored rather than just following the herd right now. And I'm going to start by talking about exploitation. We're in an age of hypnotism, I call it, where everyone gets hypnotized by the hype that happens about AI. Success in AI are overhyped, distorting markets. And I wrote this before Tuesday, when Google released a new agent, Bard, and their stock price dropped 8%. Craziness, total craziness. It gives false hope and false fears. So we need to be careful about that. But there are real kernels of success that can be exploited in robotics and other places. And I want to talk about that. And we can make our current paths move forward more quickly. And then I'm going to come back to, but there's some real problems deep down that we need smart people to figure out. And that may take 300 years. So it's not instantaneous. So AI has a long history of overpromise and under-delivery. John McCarthy, one of the founders of AI, thought in 1962 that we'd have human-level intelligence by 1968 with the computers then. That didn't quite work out. And, neural nets, you can put that in there 3 times. Neural nets were going to solve everything. Maybe they did this time. Maybe they didn't, but it's different. And so on and so on. All these things turned out to overpromise and underdeliver. Generative images, large language models, maybe it's overpromise and underdeliver. We got to wait and see. But there's a lot of hype about it right now. And I think people just should calm down. So Many successful AI applications have a person somewhere in the loop. And that's certainly true of these large language models. It's a person reading what it is that says it's successful or not. In Google search, before they filled it with ads at the front, it gave, 10 interesting results and you selected which was the right one. So you were in the loop. And a lot of AI stuff has a person in the loop in some way. So the success is not just the AI system, but it's this AI system and the person together. But robots who are moving fast, there's not necessarily time for a person to get in the loop. So robots have to be righter more, which means if you want things to be righter more, my grammar's really good, right? If you want things to be righter more, then you maybe need to scale back your expectations so you don't go into dangerous territory where it can't be right. But at the same time, I think people in robotics underplay the fact that there will be humans near the robots at all times. The humans are part of the system. There's very few places where it's just robots and nothing else. Maybe in Silicon Fab, places like that. But most of the robots, wherever going to see, there's people around, and we have to interact with people, and we have to think about people early in the design process, because gluing the people onto the robots later generally doesn't work well. I want to talk about what I've called the 7 deadly sins of predicting the future of AI. I'm just going to go through some brief examples here to give you an idea of these sins where we humans get it wrong in predicting AI. And I want to have these here because then I can refer to them. You can find this there's an edited version in Technology Review, or you go to my blog and it's there, me being really wordy without an editor. I first want to talk about suitcase words. And this is Marvin Minsky's term. And here I blame the press offices at universities and companies. They're always saying, our team at such and such a lab just developed a robot with a sense of touch. What's a sense of touch mean? Is it just pressure? Is it hot, cold? Is it knowing when something's wet by, differentiating the temperature gradient? Touch, can mean many things. And so, one of the favorite things is the system can learn. And I've had my VCs call me up. Hey, such and such has a robot that can learn. Can your robot learn? Your robot better be able to learn, otherwise you're going to get beaten. Well, what does learn mean? Learn's a big word. We learn to play tennis. That's one sort of learning. It's a little different from learning to ride a bike. Certainly different from learning Latin, which is different from learning algebra. You can be good at learning algebra and lousy at learning Latin, or vice versa. Learning chess, that's a different sort of learning. Learning to play music, it's another different one. Some of these things I'm good at, and some of these things I've just gone through, I'm really lousy at. So learn's a big word. You get to a new city and you learn your way around the city. Learn is a big word. And when we hear that there's a certain capability with a word associated with it, it can mean all sorts of stuff. And then people get confused because they think, I can learn. It can do whatever. Learning programming, different. Performance versus competence. This is, I think, our biggest mistake. We humans are really good at evaluating a person's performance on a task and then knowing what they're likely to be able to do around that. So if I see a person in the middle there looking at a picture of people playing Frisbee and he says in English, oh, that's people playing Frisbee. That's a performance. I think he probably has a competence to speak English. I think I could probably ask him about what's the weather like in the picture. Is it fun playing Frisbee in a snowstorm? Well, what do you mean by fun? So you expect that they can round out stuff, but many of our AI systems are not having that general competence. They're having a performance, and we make a mistake. The people in general make a mistake. We see the performance and we apply the model that works for humans of how that performance is an indicator of competence, but it's not necessarily in the system's the artificial systems we have. Exponentialism, for 50 years, we had a singular event, I think, in human history, exponential growth in computer power for 50 years solid. And it's trained us to think everything's exponential, but not everything is exponential, and everything certainly doesn't stay exponential for 50 years. So we see some increase in performance in something, and people say, oh, that's going to get to be superhuman. But there's always an asymptote. Maybe the asymptote for that technique is at 30% of human capability. Maybe it's 50%. But there's a tendency to think, oh, the asymptote, it's probably not even an asymptote. It's going to be exponential forever, and the world's going to blow up in a singularity. So we tend to think that it's going to get superhuman when we have no evidence that that particular technique is going to be superhuman. And lastly, indistinguishable from magic. If some technology is so different from what you understand, you can't know the limitations. So people can sort of hypothesize, oh, but it'll be able to do this. Oh, but it'll be able to do that. And it becomes magic. You can't argue against magic, but that's what happens quite often. People ascribe such power to the technology. So when I talk to people about particular technologies, they say, oh, you don't understand how powerful it is. I read about it on the internet. It's really powerful. You don't understand. Oh, and lastly, speed of deployment. We see something and we think it's going to, and we've seen that in the last week with these chat GPT, et cetera. It's going to change search forever, and it's going to change it now. And the companies are rushing out to try to ride that, some successfully, some unsuccessfully. But deployment takes a long time. Here's a question for Dan Kotychek. No one over 30 can answer this question. When did a self-driving vehicle first travel 20 kilometers? Oh, I changed that. 20 kilometers, not miles, at 90 kilometers per hour down a public freeway. I can't hear you. I can't hear. You are not supposed to answer. I said people under 30. You're not under 30. Dan. I actually can't hear what he said. So, what? Yeah, right. So when did it first happen? When do people think? If you're under 30, you can answer. When did we first drive down a freeway, an autonomous vehicle, and a public freeway with other cars on there, 90 kilometers an hour for over 20 kilometers? When do you think that happened? What? 60 is a good guess, but not quite. First paper with a car driving on an open road was 1979. But the first time it went this well was Ernst Dickmann's. And I don't know if that's what you were saying, Dan. I can't hear you. Sorry. I got my hearing aids in. I still can't hear you. I'm honest about it. So it's been around for a long time. And what happened was when the DARPA Grand Challenge happened in 2007, people saw cars driving around. They said, oh, it'll be deployed instantly. It's going to happen. It was already 20 years old at that point. Things take a long time to deploy. This is a slide I captured March 27, 2017. It's still there if you go to that page. This was predictions made about self-driving cars. So let's go to line 4. The Ford CEO announces fully autonomous vehicles for mobility services by 2021. He announced that in 2016. 2021 I've outlined in pink because that's gone. It didn't happen. Ford does not have fully autonomous vehicles. And the orange arrow is where I know that they later revised what they said. But every date that has passed there, it didn't happen by. And Elon announces every year that by the end of the year, it's going to happen. There's a great video from 2014 showing clip after clip, year after year, of him saying that. So people thought that deployment would happen quickly. Now, deployment is happening. I'm going to talk about my experience with deployment, but I want to say another thing, because this is really coming back to bite people. RAB, that's me. This is something I wrote in 2017. you know, that a driver doesn't just drive. They do other stuff. They refuel a car or plug it in. They remove things left behind by a previous passenger. This is in a ride service. Bottom one wakes up drunk passengers, and that is relevant today. And on the right, when I say informal maintenance of the car, that's clean up the vomit from the drunk passengers. So they do a lot of stuff besides pure driving. We'll come back to that in a second. Oh, there's another one on interaction with pedestrians and other drivers. On the right side there, self-driving developers were ignoring dealing with the dynamics of the pickup and the dynamics of the drop-off, because you need that for a driverless road service. So I took my first, I'd been in a Waymo car 10 years ago, but I took my first actual driverless ride where there was no one in the front seat in May of last year. This is in a Cruise vehicle. I live in San Francisco now. I cannot walk out my door and walk 100 yards at night without seeing a Cruise or a Waymo or a Zoox. San Francisco is infested with them, just infested with them. Now they have human drivers, the training data. But since early 2022, Cruise has had a license to do fully driverless rides in the city between 10:30 p.m. and 5 a.m. About half the nights, the service gets canceled. I don't say why, but I do notice it's when there's fog around, it gets canceled. I do notice from the app, they probably have about 32 vehicles doing this. By the way, they're losing $5 million a day at the moment. That's been public. So here I am. I've called my vehicle. It didn't come to my street because my street's really steep. So it said, come down to this other road where it's flat. I went down, got in the car, opened it with my app, and we went off for a ride. It was about 2.4 miles directly. It went 4.8 miles. It really went out of its way to avoid any place just about where there could be any busy traffic. I think that's smart because they don't want a horrible disaster. Didn't do left turn, unprotected left turns against oncoming traffic, would loop around in a right-hand turn loop to get to other places. The one time we were on a road with two lanes of traffic, it reminded me of when I taught each of my 4 kids to drive. Slamming the brakes on, almost getting hit from behind. But it worked, and I got to say it worked. Here I am on my 3rd ride of the night. I'd been across the road, I'd called it, and it decided it was going to pick me up on this side of the road. And you can see there that there's construction on the left blocking the sidewalk completely. So the car pulls up, and it's out in the traffic on the right there. So I'm standing where there's on the sidewalk, waving to it. I knew it wouldn't work, but I had to do it to say, come here, come here. And of course, it just sits there. So I had to walk out in the traffic because it didn't have the pickup. It didn't know about the construction. It wasn't in its map, so therefore it couldn't react to it. Now, this is a story from less than 2 weeks ago in San Francisco. Robot cars are causing 911 false alarms in San Francisco. 911, 911. What are these false alarms about? Well, Cruise staff called 911 after a passenger in one of its driverless vehicles became unresponsive. Police and firefighters rushed to the scene, but found the passenger had fallen asleep, i.e. was drunk, most likely. After 3 of these, the 911 said, not our job, you can't do this. And well, this is the public relations people. In response to a question, she wrote, suggestions that Cruise shouldn't err on the side of caution to ensure that passengers who are unresponsive are safe is something we strongly disagree with. Well, I strongly disagree with you having a business model which requires you to call 911 all the time. If you're going to take someone into your car, you should understand when they're asleep and when they're not asleep. It's your responsibility. It's not the responsibility of the overstretched city services. So here, deployment, interacting with real people is much harder than just driving on the road, and driving on the road is pretty damn hard. And here's another thing that's been happening. One of the companies, robo-taxis, drove over a fire hose at an active fire scene. They don't know there's a fire going on. There's flashing lights. They just drive through. A human driver's not going to drive through when there's a fire. And so another case, they saw a driverless cruise vehicle approaching, made efforts to prevent it, waved, no, it keeps coming, keeps coming. They had to smash the windows. That's what firefighters do in San Francisco now. When they see a cruise nearby, they smash its windows because they know that's how to stop it. So deployment is harder when there are people involved. And we, as robotics people, need to think about that. What are we going to do with these robots? Where are we going to put them? How are they going to interact with the people around? That's really quite important. When I write something in blue here, it's advice for you. Remember the people. Always remember the people. You know, you like your equations, your argmaxes, and all that stuff, but there's people going to be in the system. Think about the people. Successful robotics deployments are in general human-centric. And so you have to think about the humans. The Roomba, which we introduced in 2002, it was worth, the company's worth $3.7 billion. That was just and there's 35 million robots deployed. Not a single injury ever caused by one, even though people have tried. We had cases of, they said, my Roomba caught fire and burnt down my apartment. In each case, we got the physical evidence. You'd see that it was being put on a hot plate till it caught fire. Another one with scorch marks from a blowtorch to set it on fire and then have it burn down the apartment, etc. But we interested in 2002. And then we had to evolve it because in 2002, we were just, computer geeks from MIT. So we had that little on-off symbol that we sometimes have on computers. People didn't know what that was. And there was a rocker switch in there. It had 0 and 1 on it. People are like, what the hell is that? We don't know what that is. And then here, there's these 3 buttons, S, M, and L. Now, remember, no one ever reads a manual that comes with anything. What do you think S, M, and L stand for? Small, medium, large. So one was for a small room, one's for a medium room, one's for a large room. How big's a small room and how big's a large room? So over time, the interface evolved, and there on the right is pretty much the current one. There's a green button in the middle that says clean. And I use that too. You just press clean and it cleans. Now, hidden below that, there's a row of 4 buttons where you can go in and act like it's your old digital watch and try and figure out the interface and get it to come out at 2:15 p.m. every 3rd day and stuff like that. But for most people, it's just clean. That's the important interface. And one important thing we did right from the start was we had a handle. Didn't tell anyone what the handle was for, but people know. If the robot looks like it's gets stuck, they know they just go grab the handle and they move it 2 or 3 feet. Then it's unstuck. Didn't have to train the people, but it gave them an affordance. Handle means this is a grabbable thing that you can move. A robot, bomb disposal robots in Iraq and Afghanistan, which people loved. This is one that blew up. You can see on the back of the head on the right, they'd been recording how many IEDs, how many UXOs, VBID, vehicle-based explosive device, etc. And this one blew up, and the guy brings it into the depot and says, you need to fix Scooby for me. We can't fix Scooby. We'll give you another one. No, Scooby and I have been through a lot together. And we were astounded by this. We did not expect Marines to be doing this. But an MIT engineer, who will remain nameless, Pavlo Rudikevich, built this interface. It's menu-based. You can do anything with the robot. Who were the users of the robot? There were 19-year-old kids who just graduated high school, joined the military, got shipped to Afghanistan or Iraq. Well, we had manuals. The Rapid Equipping Force removed the manuals before they shipped them because they didn't want the enemy to see the manuals. So now these robots arrive, and these 19-year-old kids, what am I doing? Answer, we built a hardened Game Boy controller. Now they all had 10,000 hours of stick time without any training. And now they could use 80% of the capability of the robot. Our engineer said, oh, but they can't do such and such. Yeah, but before they could do 0. Now they can do 80%. That's a big win. And then when Fukushima happened, we got robots to Japan within 24 hours because, surprise, surprise, the beautiful walking Honda robots were not able to do anything in Fukushima. We'd had robots in Iraq and Afghanistan for 9 years. We were able to quickly train the TEPCO people, and they used the robots in Fukushima to understand what was going on. By the way, the middle top there is the world's biggest Roomba. It's a 200 kilogram, one of our robots with a vacuum to suck up radioactive stuff. So as you're thinking about robots and an application, figure out how to make it effortless to get robots to do what people want to do. That's important. Most robots are not like this. Here you've got no people, just robots. There's a little cage there for the people to be in to keep them away from the robots. Most robots are interactive. And at my last company, we had collaborative robots which people could interact with. We made them safe to be near people with no cages around them. We taught by demonstration, not by showing people through vision, but by grabbing the robot and moving it around. And then, bring your kids to work day. We just let kids, play with the robot. They soon figured out how to program it to do stuff. No manual, no training, because we made it very simple to do simple stuff. And, kids didn't know that they had to be particularly scared of robots, so they're feeling okay to interact with them. They understand them. They understand how to move them around. They understand how to teach them to do stuff. But for complex stuff, that was good for many assembly line workers to program the robots. But for really complex stuff, we had to give another level of interface where as you move the robot around, it built a behavior tree, a graphical program, and then the engineers could go in and edit that. So different people need different stuff from robots. But you must think about that. Who's buying the robot, who's using the robot, how's it all going to work? Let different people interact differently and in ignorance of the other ways of interacting. This can help you have a human-centered robot. And I've hacked together some pieces from a longer video. This is my current company, Robust AI. It shows what we're doing. And it's me and Anthony Jules, the CEO, talking here a little bit. Building a new iconic class, Carter. Carter's a new type of robot. It's built not just to work near people, but with people. It can complete its work autonomously, but at the same time it's responsive to people and its surroundings. And then with a simple touch of its handle, it changes modes. It becomes the ultimate power tool for any user. Carter's handle enables people to maneuver it intuitively, allowing them to move heavy payloads with ease. And they don't have to be trained. They just have to see someone else use it, but they know how to use it. Many autonomous mobile robots, or AMRs as they're called, make people feel unsafe and unseen, making operations less efficient. What we do is put people first, and we've built robots to empower them. A truly collaborative mobile robot that moves in coordination with people like a responsive dance partner. Carter works with you, moves with you, and flows with you. In the future, that's how mobile robots should be. They should know about us as people, and you should be able to go and grab them and change what they're doing. Together,
we built Grace. Grace is a software suite that allows facility managers to quickly introduce automation without changing anything in the environment. It reduces the time and effort teams spend on fetching, pushing, and parking carts, and Grace is easy enough to use so teams can use robots to support even short one-off jobs. What if you could design and deploy user-friendly automation for your company in a day? With Grace, you can map an environment with a phone or tablet, build a digital model of your facility. With that model, you can create and simulate material handling workflows from a web browser, doing in hours what typically takes months. Once you like what you see, you can deploy a workflow instantly to people and robots. Whether your job runs for years or days, you can get it up and running in no time. For example, you could give and track people, locations, and objects. Our robots don't just move through space like other robots, seeing everything as an obstacle. They understand many things in the world, like people and congestion, so that they can.
So that was hacked together of a fundraising deck. By the way, worst time in 20 years to be raising funds. The point I wanted to show you there was mobile robots deployed in the world are often just switched off, or worse, somehow they got in the way of a forklift and the forklift drove right through them, which happens often. Or in hospitals, Aethon robots, you find them off to the side, switched off, and you ask the nurses what happened. They say, oh, it broke, we switched it off. No, what really happened was they were running down with a patient on a gurney. The robot was, taking the dirty sheet somewhere. It saw something it didn't understand, so it stopped and blocked the way and really caused problems. So what we have done with our current robots, you just grab the handlebar and you can move it. And you get control. So people have control. So they're not at the mercy of you engineers and what you think is important and what made your job easier, but they get to control what their job is easier. And then at the end there, you saw things colored. And so we have semantic labeling going on. That's a pallet on the floor. If there's a pallet on the floor, it's probably not going to move by itself. So don't just sit there and wait for it to move. Go somewhere else because it's going to sit there for a while. Ladders, bad news to hit a ladder because there's probably a person up it, etc. So semantic understanding, and I'll get to semantic labeling in a minute. So what's new to exploit in all these robots? Deep learning has brought new capabilities to AI. And I think it's a golden age for designing silicon. For the last 50 years, because everything was going to double on a predefined frequency, no one dared do anything new because it would get beaten by regular software on the faster computers. Now, some people did. Japan had their sixth generation computer running Prolog, which didn't work out. Danny Hillis at MIT built a connection machine. 3 years later, it was beaten by regular silicon because it just got better and better so quickly. But now that law has broken down. And so now there's people doing really interesting stuff with silicon. Some of it is really low power to run on little tiny drones. Others is putting teraops right next to cameras. And so you can run models on cameras. So computation is moving towards cameras and other sensors, and it completely changes the architecture. Now, and that's, what's his name? Gretzky, Wayne Gretzky. You ask Wayne Gretzky, why are you so good at playing hockey? I skate towards where the puck's going to be, not where the puck is, was his famous saying. So skate towards where the puck is going to be, where the silicon is going to be in 2 or 3 years, and you'll have applications that work. Massive amounts of cheap computation. Now, there's some common misconceptions. Deep learning, computer vision is human equivalent. Yeah. Actually, convolutional neural networks are texture biased, whereas human vision is shape biased. So there's a fundamental difference there. Computer vision can recognize objects. Computer vision CNNs can label image regions. Maybe it's not the same as recognizing objects, but they can do it really well. So exploit what's really there. Understand that it's not the conception that might be around, but the stuff it can do, and use that. People often think running neural models is computationally expensive, but now you can run them right next to the camera, and you can have lots of models running. Learning is still an issue, but running the models is cheap enough to do for a few dollars, actually, at the camera. And localization indoors must use LiDAR. People still think, but in fact, Visual SLAM is a reality. So again, run with this. These sorts of things are there. It's computation. And in general, computation versus other mechanisms. LiDAR is getting replaced by VSLAM. mechanical thing getting replaced by VSLAN. You can often fingerprint individual gear trains, instances, and trade more computation for reduced mechanical precision. Not always. With real-time solid-state sensors, you use computational control loops in trade for reduced mechanical precision again. And with better forward models of what's about to happen, having a good model of dynamics with equations, knowing what's happening, you can recognize anomalies without additional sensing. So the robot arms I showed you from my last company, I would, maybe this was foolish of me, I would just go up to any of our robots and put my head in the way of it as it was swinging and let it bash me in the head. And I guess the engineers thought I was important to the company because they could have just, it could have been bad. I would not do this with a universal robot, by the way, but with Rethink robots, I did it. And how did that work? There was just about 1 millimeter of rubber there, and suddenly the forward model is looking glitchy, and it just sucked all the energy out of the system as quickly as it could and came to a halt, and I'm still okay. Now, when I'm saying this, you'll notice if I get to the end of the talk that there's an inconsistency with what I'm going to say later, where I dish on computation. But I say you should be the octopus. Move computation to the edge. Octopus's legs are independent of their brains, largely. They can do all sorts of stuff. Move computation to the edge, and you'll get much better performance. Now I want to make our heads hurt a little bit. Not by being hit by a robot, but being hit by philosophical ideas. Things in the world are objects. Good old-fashioned AI, GoFi, talked about the symbol grounding problem. To what does a ladder really refer? What is a ladder? What does it mean to be a ladder? That got brushed over with current deep learning, but we'll come back to it. Some people think deep learning nailed it, but I don't. And then there's also the problem of stability of the grounding. How a symbol, a label, involves ongoing perceptual smoothing and integration, because these deep learning networks will flash things off and on. You got to smooth over it. But maybe there's something deeper going on. And if you want to make your head really hurt, read this book by Brian Cantwell Smith, who did his PhD at MIT in the mid-'80s, wrote an 800-page thesis, and the pencil in the DSpace library says volume 1. This is his shortest book. It's only 165 pages, but it's really hard to understand. But I'm going to tell you some of the key ideas here. He says that we, humans, have these Cartesian assumptions about intelligence. It's about thought, meaning, sort of rational deliberation. You can reason from one thing to another. And you see criticisms of the generative language models not getting that reasoning right. There's Twitter wars. This is really important stuff. It's really good. This is really stupid stuff. So look at the stupid stuff examples and you see where it gets wrong. The ideal model of thought is logical inference based on clear and distinct concepts. What is this? How does A imply B? They're clear and distinct. And perception is at a lower level than thought. It's going to be easier. But the ontology of the world is what Brian Cantwell Smith calls formal. The world is made up of discrete, well-defined mesoscale. Mesoscale means not a little quantum thing, but a thing like this, the sort of stuff we talk about all the time. It's made up of distinct mesoscale objects. That's what the world is made from. It's sort of assumed, with properties and standing in unambiguous relations. And then traditional representation in AI assumes that the system works mechanically. There's no elixir of life or soul. It's a process, it's a computer algorithm. The system's behavior and constituents support semantic interpretation. What are the semantics of that object I'm seeing? And then he says the system is normatively assessed. I'll explain that in a second. Then he says another one, they're not effective. What does he mean here? He sort of means that we all agree on what is in the world. You and I see the world the same way. You think this is a microphone stand. I think this is a microphone stand. You think this is a little screen. I think this is a little screen. We sort of agree. There's a normative understanding of the world. And any AI system should have that same understanding if we're going to interact with it. And then the last one means that the semantic relationships between objects in the world are not immediately mechanical. There's something in our thought process. The fact that this is a microphone stand and has a relationship to a microphone is not a perceptual quality. It's that you know you put the microphone in the microphone stand. It's some other knowledge you have of the world. So what Smith says is, you know, he describes what a system should do in terms of this P1 through P4. But CNN, convolutional neural networks, and deep learning try to get at C3 and C4. They try to have this low-cost computation model recognizing, which brings out things in the ontology, maps to symbols that it labels. And transformers, which are the basis of ChatGPT, et cetera, are trying to get at, you know, what are the ways words and semantic concepts are used in the world and what is shared. And it comes at it through language. So they're trying to get at that. But it gets tricky. So here's an example that I have in my company. We're looking at palettes. They're both palettes, right? By the way, they're very different palettes. The one on the left is a 2x4. You can two directions you can go in with a forklift from two ends to lift it up. The one on the right, you can go in 4 directions to pick it up. So they're different. They're both palettes, though. They've got palletism. Well, does your deep learning network also, that you trained on plain wood pallets, also handle red pallets, blue pallets? Maybe it gets a little confused. And what about this? Is that one on the left a pallet or not? It's actually a 4x4, but a different sort of 4x4, but it's broken. What about on the right? When does something stop being a pallet? It's not a distinction. It's not a distinct stop, right? You know, if you grind that up in a wood chipper, you won't be able to recognize palletness anymore. But you can go in there with a sledgehammer and do a few more whacks at that pile on the right, and we'll still say, yeah, that's a pallet. We might even be able to say if it's which ones are 2x4s and which ones are 4x4s. We may be able to do that. So it's not a distinct thing by itself. It's a reasoning, an interaction as we think and imagine what's going on with it. So Smith says that what's broken is that our idea that the world is made up of distinctly labeled or named mesoscale objects is wrong. He says that representation is not a simple map from the world to some symbolic domain or ontology. Rather, objects are registered in the world through an ongoing process. So there's a mapping and an ongoing process. It's not a static thing, which is a radically different way of viewing representation from what we've all been doing for the last 50 years. Maybe he's right. Maybe he's wrong. Maybe ChatGPT will handle P4 and make it right. I don't know. But these are deep questions about the way we use representation. So if you're building a robot and you're using deep learning, be aware of the limitations. You might say, oh, I'm getting a view of the world, but it's got limitations what that view of the world is. And you may find yourself trying to, turn the handle and get finer and finer distinctions which just aren't in there in your representation because it's a broken representation. And I think it's important to think deeply about this, which gets me to, well, if this isn't all right, what could be right? And that's exploration. And very few academics do exploration these days because you don't get funding for it. You can't start a company with it. No one talks to you because they think you're the crazy one in the corner of the lab. Students don't want to work for you because they don't get jobs. But boy, if you got it right, you could be famous. So what are you willing to risk? How much? So, yeah, I've got time. So this is from a road near my house. If I go out on the freeway, I see better examples of this, but I don't like standing on the freeway to take a photo. But what do you notice about this? There's a road to the left of this white line, and that's where the traffic drives. And to the right there is the edge of the road. And it's just covered in sticks and stones, and the main part of the road is not covered in sticks and stones. So how do the sticks and stones know to move out of the way? Did they compute? Did they compute how they should move? Or was it because the cars kept knocking them and they randomly got thrown up, and if they landed on the side of the road, they didn't move again. If they landed in the road, then they got hit again at some point. So is that a computational process to clear the road? I claim it's not a computational process. Now, one of my least favorite people is Elon Musk, but I'll use him as an example. Oh yeah, so did the stones and sticks and leaves compute? Did passing cars engage in computation? No. So and he's done great things, Elon. Falcon 9, May 2020, carrying 2 passengers to the space station. First time humans launching on. Okay, when Elon decided he was going to do satellite launches and launch people, did he say, I don't need to build robots. Build rockets. I don't need no stinking rockets. I'll just write a computer program, and that will get people into space. No, that doesn't get people into space by itself. What if he wrote a really big program, and he used a bigger carbon footprint than the rocket? Still wouldn't get people into space. Now, that doesn't mean that his rockets don't have a lot of computation on board. It doesn't mean that he didn't simulate them computationally ahead of time. But to actually get into space, you got to burn rocket fuel. You got to release energy in a particular sort of way. It's not a computational process that gets you into space. Yes, you use computation, but that's not the thing that gets you into space. It's not purely a computational problem. It's something around physics of some sort. Here's no matter how well you simulate with computation, it still doesn't get people into space. So we've got these brains out there. Are these computers? Well, they're pieces of meat. That's one thing. Are they meat computers? Are they doing computation? Is computation what they do? Is thinking or even controlling a creature a computational problem, or is it more like kicking the sticks off the road as an analogy? Is a jellyfish computational, or is it just some control loops, analog control loops? What about a tree? Is that computational? But it finds sources of food, finds water. It knows about. It does kin recognition. It does all sorts of things. But is it a computer? Is it doing a computation? Are they doing something else? And just like if you simulate a robot, really, really heavy duty, it still won't get people into space. If we use computation really, really a lot, are we going to get cognition? We sort of all think that's true. But where did that idea come from? And computational brain, computational neuroscience, that's where it's at. But we know that, we've been trying to simulate weather. We still can't even predict weather computationally, let alone control it. So it turns out that what we call computation is a socially constructed thing, and I'm going to show you how that came about. It roughly describes what things we call computers compute and has enormous intellectual field behind it, enormous economic. But many things in our world are not fundamentally computation. Computation can be used as a metaphor, but is that the same as something being computation? And when we do a simulation, are we only simulating certain aspects of the phenomenon? We don't know whether the things we call computers can be as cognitive as a jellyfish, and a jellyfish is not particularly cognitive. So I sort of blame John McCarthy for this. I don't know whether Rosina said she was going to be here, but Rosina's not here. Rosina and I both had John McCarthy on our thesis committees at Stanford. But in 1955, he wrote a proposal for the 1956 Dartmouth Conference on AI, where he first introduced the term AI. And he said, a 10-man study, notice man, of artificial intelligence. The study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. So in the first sentence, he introduces artificial intelligence without explaining it. The second sentence of his proposal says, it's computers. And then later, if a machine can do a job that an automatic calculator, which is what they were sort of called then, can be programmed to simulate the machine. So a computer is good enough because it can simulate any other machine, and the brain's a machine, so therefore it can simulate it. If it had rockets there, it wouldn't have been true, but because he had brains there, he thought it was true. And I've been worrying about this for a long time. This is a paper I wrote in 2001 for Nature about artificial intelligence and artificial life. And I said, maybe we just don't quite understand how things work. And maybe there's something else. And maybe it's non-threatening as the notion of computation. People don't get upset about computation, although I'll show you a preface in a second where people did. People don't get upset about the idea of computation being computation. Maybe there's some other mathematics that we just don't know about yet, which is a better way of describing what's going on and describe materials rather than computers. This is from my talk I gave in 1991 in the Sydney Opera House. And I wish Rosina was here because she introduced me that day. It was great. Rosina, if you're online, hi. So cybernetics was a previous way of thinking about intelligence before artificial intelligence. And rather than in terms of, it talked about all the possible behaviors that a machine could produce, not a particular behavior, which is what AI does. And down the bottom there in green, it was based on continuous functions, almost everywhere, continuous, differentiable and stuff, a different way than we have of thinking about computation. So the history of computation has been around for a long time. Heron's method for computing the square roots of a number was important for land management in Egypt 2,000 years ago. We think about algorithms in terms of writing down numbers and deriving new numbers from those written down, including side calculations. And this really came to bear. The modern era started in 1614. On the left there, in Latin, is John Napier's table of logarithms of sines and cosines, which he produced by hand. That's 1614. On the right, the 1620, Johann Kepler with his ephemeris. What was his ephemeris? It was predicting the movement of planets for astrology. Astrology was a big money maker then. You know, he was really an astronomer, but he had to make some money, so he took the money for astrology. Remind you of anyone? And then he has a little love letter in that document to John Napier, saying how much these tables meant to him. It made his calculations easier. So tables were important. And John Napier produced these 2,700 lines in the tables, 10,800 hand-computed numerals, took him 20 years, made a mistake early on. 7th decimal place was wrong in all of them because he made a mistake. Mistakes were bad. Leibniz realized mistakes were bad and said, we got to mechanize this. Didn't know how to really. At 100 years later with Taylor's theorem, where's Taylor's theorem come from? Comes from Taylor, Brooke Taylor. I didn't know. It's Taylor's theorem. And you can get you sum polynomials to get approximations to functions. And so then Babbage in 1837 had his calculating engine, the method of differences, which was to basically compute Taylor series, to compute tables, which are needed for engineering. And the thing I didn't realize about it was that it directly produced the printing plates. So no human ever touched those numbers because they knew humans suck at calculating and copying and doing stuff. So he tried to do it mechanically. This is a replica that was built later. He never built it. There's another replica. You can find all sorts of replicas online. It works. But then he came up with the analytical engine, and Ada Lovelace talked about it at great length, greater length than he ever did. And it's just like today's computer: a central mill, an ALU, a sequencer, punch cards, loops weren't quite there yet, and a storage unit where many variables could be stored, and input-output facilities, so humans didn't touch the output, they got printed directly. And this is the first program ever written. It's written by Ada Lovelace. It's 23 statements in it, although she doesn't have the control loops there. She just talks about the control loops, so it's sort of a trace. But the beautiful thing about this, well, it calculates Bernoulli numbers, but the beautiful thing is it's the first program, and it has the first bug. Arguments to divide were the wrong order. because of course you didn't get to test it on a machine. So Alan Turing came along in 1936. He was this young kid from Cambridge. He'd just screwed up his bachelor's thesis. He wanted to do a master's thesis. Hilbert had a new set of problems, 3 problems on completeness. I'll get back to it in a second. And decidability of certain problems in mathematics. And the hypothesis was whether or not there was a mechanical process where you could decide statements in mathematics were true or not. So Turing decided, instead of inventing a machine that can make that decision, I'll just prove you can't have a machine. That's an easier hit. So he had to hypothesize something and argue it was the most general process mechanism possible, and then show that it couldn't decide these problems. So he sort of had to set up a straw man that he could knock down. And Gödel had already knocked off consistency and completeness with some different methods. So Turing didn't have many good arguments of why his Turing machine was the ultimate computer. On the other hand, it's sort of stood the test of time. It just led to a few little things, and there he is on the Bank of England 50-pound note. But he modeled it after human computers. At the time, computers were humans. And if you look at them, you see computers were also female, except for the boss and one guy in there. And what they did was follow rules with paper and pencil, and they've got some adding machines here, and compute tables. Crank out tables like Napier did. And in 1945, von Neumann says about his machine, EDVAC, it's just a computer, meaning it's just a human doing that stuff. So computers were humans back then. But Turing can't really prove that what he's got, this mechanical thing, is what computation really is. Justification lies in the fact that human memory is necessarily limited, so I'm going to have limited memory in my machine. Fundamentally, I appeal to intuition to argue why this is how you do stuff. So let's use intuition. And people struggled for decades over whether Turing computation was it. Now we accept it, but and along the way, Moore's law happened and things got better and better. So they sort of got tired of worrying whether this was it. Marvin Minsky in 1967 said that, a specification of how a physical object ought to work. And he said, maybe it'll get emotionally angry at me talking this way up in the top there. But he decides that an effective procedure can be realized by a Turing machine. He used intuition for that. Donald Knuth, in his books, said, all the operations be formed in the algorithm be sufficiently based that in principle they can be done exactly in a finite length of time by a man using pencil and paper. That's what computation is, what a person can do using pencil and paper. And it's clearly effective because experience shows that it's also powerful enough to do anything that we can do by hand. Intuition again. And so on with Hopcroft and Ullman by 1969. They were saying, this is what computation is, probably intuition. And by 1974, everyone sort of agrees. They gave up. Yeah, Turing was right. That's all there is for computation. That's what we call computation. I'm going to skip over some stuff here. But in the period 1945 to 1965, 4 disciplines emerged: neuroscience, abiogenesis, that's science of thinking and being, and engineering, artificial intelligence and artificial life. They all formed in that 20-year period. There was lots of interaction between people, and everywhere there's an arrow, I can point to someone who worked in both those fields. And they chose, for 3 of those fields, computation as the primary metaphor or analogy. But does that mean they are computation? Is neuroscience really computation or not? And I'm sort of astounded by 2 things. Turing's definition of computable was what machines compute was what people could compute. And wait, computers are people? I didn't realize that. And then with computational neuroscience, wait, people are computers, meaning our modern computers? There's a circular thing going on here. It makes us all happy, but is it right? And I'm not going to go into any more detail here, but Claude Shannon and Warren McCulloch and Pitts were key people, and then von Neumann was involved, John Holland, E.F. Codd, who actually won a Turing Prize for databases, et cetera. And Warren McCulloch who some people might know was at MIT for many years, wrote a very influential paper, two influential papers, one on the logical ideas of a brain, but he just made that up. It says it's logic gates. The brain is logic gates. Just made it up. And his other paper was with Letland, Maturana, and Pitts, where they examined what a frog was doing and what it was doing in the terms of using its vision. It was the first paper on functional neuroscience. And he had a whole posse of people who went off and influenced the world, that computation was what's important for AI. He had John McCarthy when he was younger, he had Minsky, he had others. And that is how computation has come to be what we think intelligence is. But I question whether that's correct or not. And I think I'm up in time. I'm not going to explain polyclad flatworms, but it's a great story. I'll tell people offline. Oh yeah, here's the thing. It's really important to figure this out, but if you decide to try and figure this stuff out, it's going to be a lonely life and you'll live in penury, but I hope someone does it. Please. Okay, I think we go to questions now. Now, Dan, you can speak. Over 30s can speak now. You can ask a question.
So I'll be taking questions from the in-person audience if you have questions. Okay.
So great talk, by the way. Thank you. Could you just kind of explain what you mean by computation? Because what I don't get is the gap between the physical rocket and our computed rocket, because the math underlying
the computer rocket won't fly into space.
Sure. But the underlying math it took us to get there is the same, right?
Oh, except for thermodynamics.
I mean, so you can argue at some point we don't have, our math's not good enough, or we don't have enough.
Yeah, but my point about saying this is computation doesn't make the rocket move.
Sure.
Okay?
Right.
But we think computation makes brains think.
So I guess, okay, I get to add to my question.
That's a different. So
what do you think about like analog computation?
It's not about computation. It's about whether
I'm not getting is what is the difference? Like,
well, is a rocket engine with burning fire different from computation? Would you give me that?
I do not. I think we should.
Oh, you're a computationalist. You're one of them. You're a computationalist. You're so in the way of thinking that you think everything's computation, because that's what I do. So it must be. No.
I don't see where the difference is.
Okay, I've got a really powerful computer.
Yes.
Does it go into space?
Does not.
Right. That's the difference. But if you say, oh, burning rocket fuel is a computation, then computation is meaningless.
I mean, so the difference I see is just the instantiation of these physical properties that we derived, right? In one case, we've instantiated as in.
But what makes you think that, instantiating it as a model of a person writing down numbers on paper is not missing anything? I'm sorry. See, this is the problem. We are so baked. We are baked in. Well, it's like phlogiston. It's baked into us. We can't get past ourselves, and that's my point. And you're, by the way, you're not alone. No, I'll just tell you. Sebastian Thrun thinks I'm completely off my rocker, so I'll put you in the Sebastian Thrun camp. No, I can't convince you if you can't make a distinction between a physical process and computation. You say we'll just call the physical process computation, then I can't convince you. You're unconvincible. Emulate, but it doesn't get you into space. You can emulate as much as you like; it still won't get you into space. Yeah, but that's different from the computation being the process that gets you into space. We're not gonna come to a conclusion here. So I'm gonna let Dan attack me.
Rod, thanks for your wonderful talk. If I were to have given the talk, which I didn't give the talk, if I were to have given the talk, I think astonishingly to me, I might have said many similar things. I think what I understand from your talk is really true, that there's this thing called work, and you got to do work in the world, and how do you do work, and what's the computation, if there is computation. And the other thing you said that I think is very, very important is the ontology of the world is affordances if you're going to be working. Okay, so far so good. In your day, as an academic, in my day, in your day, you were also the champion of compositionality. And my worry in what you have said today is that by casting aspersions on computation itself, you've obscured the importance of finding compositionality in things like affordances and in the programmability, if not the computationality, the programmability of work. And so I wonder if you agree with some of my complaint or how you feel.
Yeah, so I did two things. The first half of the talk, I talked about how to use computation and exploit stuff. And I allowed that maybe even ChatGPT was getting stuff right in a way that I don't understand. So maybe we don't, my point is we don't know. On compositionality, certainly, that's one of the great things about, and actually it wasn't in Turing's model, but as soon as you generalize a little bit, you get compositionality. So what became computation by the late 60s had compositionality, and compositionality is an incredibly important thing. In a longer version of this talk, and in a book that would come out if my current company wasn't consuming me, I talk about how perhaps what we're missing is a mathematical understanding of how different processes interact. And we don't have good language for that because we're so held up in the computational simulation of it instead of the mathematics of how two different processes by themselves, this process works this way. By itself, this process works this way. When you bring them nearby, they interact and interfere in a way which either or is magical. And we don't have any mathematical way of understanding what that interaction will be or a language for talking about it. And so I actually think compositionality may be in a mathematics of compositionality, which we don't have a mathematics of compositionality, a process could be important. What? I was being much more general than just those two special cases. I don't think we, and part of the talk I skipped over is we have a way of thinking which developed as in a hunter-gatherer world, where there were places, and when you put stuff there, that's where the thing is, and you go back, it's still there unless something else has interfered with it. We have our hippocampal place cells, we have our entorhinal. I have trouble with big neuroscience words. Entorhinal cortex with the grid cells, and we reuse those pieces of hardware to reason about the world, and we reason about the world in a very Newtonian way, which is why quantum mechanics hurts our head, because we're not built to reason about that. It's the mesoscale thing again. That's what we're good at doing, and we use those analogies. And you love your analogies, and I appreciate that. It's great, but they're analogies. So, yes, I just don't think we've figured it out. But that could well be, and you'll be getting Social Security soon, so you can go and work on this without worry.
So we have a question from Vijay, and he says that, Rod, great talk as usual. Thank you for the historical perspective. Very useful, not just for students, but also for faculty. Two questions. You spoke a lot about localization, navigation, and transport in semi-structured warehouse-like environments. I wonder if what you see on the horizon for applications that require manipulation.
Yes. I'm at the GRASP lab, aren't I? My last company was a manipulation company. We failed largely. At one point, I visited Jack's Hole at Stanford and saw Vic Scheinman's parallel jaw gripper that he built over 40 years ago, and it looked just like the robot hands we were selling 40 years later, parallel jaw grippers. So in terms of practicality of manipulation being anything remotely like human manipulation, it really hasn't happened. Likewise, we've gone a long way in walking robots, although they're not the same as human walking, but at least we've made progress in walking robots. We've made less progress in manipulation. Obviously, there's a big financial push on this right now. And so we see companies like Right Hand Robotics, Ambi, et cetera, building very capable hands for particular subtasks, but nothing like general manipulation. So I think someone should start a GRASP lab and and study this, because there's a lot to be done. Oh, by the way, that video I had of from my company, that first guy there with the reddish hair, he's a graduate of the GRASP lab. So Jay Davies.
He also has another question. You talked about challenges of exponentialization. I also feel that people extrapolate a lot. 10 years ago, perhaps even now with Elon Musk, Moore's law is extended to batteries, even though the chemistry of lipo-based batteries has not changed in 3 decades. Thoughts?
Well, actually, chemistry is changing in batteries, and Tesla has made some contribution to better electrodes. So batteries are getting better, but even Gordon Moore's original 1965 paper, he called out on the 4th page. No one reads past the 3rd page. On the 4th page, he says this doesn't apply to things like energy storage, because you need physical volume for that. We were just lucky that there was an abstraction between signal there or not there, and you count the number of electrons, and the signal's there if there are a big pile of electrons, and the signal's still there if there are half that many electrons, and you can keep halving until you get down to 1 or 2 electrons, and then it stops working, which is where we are now. So we just don't get those exponentials. I think it was a singular event in human history, that exponential growth of computation, which made us think it must be everything. I'm not looking.
And we'll take one more question.
Yeah, I can't hear.
Oh, okay. So you mentioned that Elon Musk was not your favorite person, and based on your experience working in the industry, I know you've headed a lot of companies, including iRobot. So I wonder, for some of us here that are interested in maybe commercializing robotic technologies and go into the entrepreneurial route, do you have any suggestion or advice that's maybe unintuitive or that you wish you had known earlier?
Well, there's certainly. You have to be a very special person to be able to continue to overpromise and fail to deliver and continue to succeed. So I do not recommend following that approach. What I didn't quite realize when I started companies was that the key technical idea is not everything you need by any means. And when you put everything around it that you do need, sometimes that key technical idea is no longer the right technical idea anyway. So you have to be prepared as you go into a company to swallow your pride and chop off the thing that was most dear to you when you started, because it may not be what is going to make the system succeed out there with real people and real customers. When I did my, I was a pure mathematician, if you told me, yes, you're going to be successful and you're going to be a vacuum cleaner salesman, I wouldn't have thought that was a good trade-off, but it's been good. But you have to be prepared to change, to pivot, and it's hard because you get devoted to your idea. In fact, Dan, you should have been aghast seeing me talk about deep learning and models and running that stuff. That's not the old me. I made him speechless.
All right, let's give our vacuum salesman one last hand. All right, that was a fantastic talk. So please tune in next Friday, February 17th at 10:30 Eastern Time for our next Grasp on Robotics, featuring Jeremy Brown from Johns Hopkins. For more information on upcoming events, be sure to follow us on social media, check out our website, and thanks again.